I changes the threat modeling conversation. Prompts, models, data pipelines, plugins, RAG, and agents all create new paths for abuse. In this module, we'll use proven techniques like STRIDE, LINDDUN, attack trees, and abuse cases to turn those risks into practical controls. We've already built the foundation: how enterprises adopt AI, how governance assigns accountability, and where AI-specific risks emerge. Now we'll turn that understanding into practice, using structured threat modeling to anticipate how attackers might exploit AI systems before controls are designed. Traditional threat modeling asks what assets exist, how data moves, and where controls can fail. I keeps those questions but adds new uncertainty: prompts, context, embeddings, retrieval, tools, and model behavior. A failure may not be a simple bug. It may be a convincing hallucination, an overridden instruction, or the wrong tool used with confidence. That means the boundary expands from securing systems to also governing trust, intent, and outcomes. Before applying STRIDE, LINDDUN, or attack trees, define what the AI system actually includes. The model is only one asset. Prompts, embeddings, vector stores, training data, inference APIs, tools, logs, and user sessions can all create attack paths. Next, trace where data crosses trust boundaries: users, plugins, providers, internal systems, and external sources. Finally, document assumptions, roles, permissions, and agent capabilities so the threat model reflects real behavior. STRIDE still works for AI, but the assets are no longer just servers, accounts, and code. Apply each threat category across the full AI chain: prompts, models, retrieval, APIs, plugins, logs, and agent actions. Spoofing may mean a fake agent. Tampering may mean prompt injection or poisoned embeddings. Repudiation may be missing proof of who approved an action. Disclosure, denial of service, and elevation can appear as data leakage, model overload, tool abuse, or unauthorized autonomy. At the prompt and retrieval layer, STRIDE becomes very concrete. Spoofing can make an attacker look like an admin or a trusted policy. Tampering can place malicious instructions inside retrieved documents. Information disclosure appears when hidden prompts, private context, or source documents leak through clever questioning. Denial of service can come from oversized prompts or amplified retrievals. The key takeaway: every input to context assembly is a security boundary. With agentic systems, the boundary expands beyond the model. The agent can reason, choose tools, call APIs, and trigger workflows, so every connection becomes part of the threat model. Spoofing may trick it into trusting a fake tool. Tampering may change instructions, parameters, memory, or responses. Repudiation appears when logs cannot prove who acted. Elevation of privilege happens when plugins or delegated credentials give the agent more power than it should have. LINDDUN gives us a privacy-first lens for AI threat modeling. Instead of asking only, can the system be attacked, we also ask, can people be linked, identified, observed, exposed, or processed unfairly? In AI, those risks can appear in training data, retrieval, inference, logs, monitoring, and generated outputs. The practical move is to trace personal or inferred data through each stage, then test for transparency, policy compliance, and unexpected exposure. Privacy risk changes across the AI lifecycle, so apply LINDDUN wherever the system touches data. During training, the concern is memorization, re-identification, and use of personal data beyond its stated purpose. During retrieval, embeddings and source documents can create hidden links between people and sensitive facts. During inference, prompts and responses may leak regulated or confidential information. In logging, telemetry and feedback can quietly become a new privacy repository. An attack tree starts with one attacker goal, then breaks it into the practical routes an adversary might take. For an AI assistant, stealing customer data could involve prompt manipulation, poisoned retrieval or training data, guardrail bypass, weak authorization, or tool abuse. The value is in the leaf nodes, concrete actions you can test. Once those paths are visible, each one can be mapped to controls that prevent, detect, or respond before the attack succeeds. In this example, the attacker is not trying to break the model in one move. They are looking for any path that makes confidential data appear in an answer, tool result, or log. Prompt injection targets instructions. Poisoned retrieval targets the knowledge source. Over-permissioned APIs target access boundaries. Exposed logs target the operational trail. Each path points to a control, such as validation, filtering, authorization, logging limits, or human approval. Abuse case modeling flips the usual question. Instead of asking what users want to do, ask what could go wrong, who might cause it, and how the system should respond. Start with the actor: malicious user, negligent user, insider, or even another AI agent. Then define the abuse goal, map the path, and specify the defense: refuse, redact, escalate, or require approval. Finally, turn each case into red team tests, monitoring rules, safeguards, and governance requirements. A common mistake is treating AI threat modeling as a model review. High accuracy does not mean the system is safe. You need to test how prompts can override instructions, how retrieval sources can be poisoned or expose sensitive data, and how agents behave when they can use tools. Any place the AI reads, remembers, calls, or acts becomes part of the threat model. The corrective move is simple: model the full system, not just the model. In the enterprise, AI threat modeling has to become a life cycle, not a workshop artifact. Bring architecture, security, privacy, data, legal, compliance, AI engineers, and business owners together. Capture the system, threats, abuse cases, attack paths, and control backlog. Prioritize by likelihood, impact, exploitability, data sensitivity, autonomy, and regulatory exposure. Then use the outputs to guide architecture, testing, risk tracking, and incident preparation. Refresh the threat model whenever prompts, tools, retrieval sources, vendors, permissions, or model behavior changes. AI threat modeling turns uncertainty into actionable security and privacy work. Stride exposes abuse paths across prompts, models, APIs, tools, and agents. LINDDUN sharpens privacy analysis. Attack trees and abuse cases make risks testable. Next, we apply these findings to responsible controls and incident prioritization.